All right, so let's talk about the current differential, or commonly referred to as the 87 protective element. So this is the most commonly used form of protection for substation buses or buses in general. And in this lecture, we'll be discussing this form of protection in a great amount of detail. So in a current differential scheme, the current on all circuits connected to the bus need to be measured, and then we're going to be comparing the currents that are entering and leaving the bus to determine if there's a fault in the bus. Now, in practical applications, this presents a problem because all the current transformers or CTs need to accurately replicate the currents that are entering and leaving the bus. And of course, we know that in reality, CTs won't replicate currents with 100% accuracy. Nothing in engineering, as we know, is perfect. So the current that the CTs replicate is not going to be 100% accurate. So there are always going to be errors in CT secondary currents. So in other words, when we convert from primary to secondary using a CT, the secondary is not going to be an exact replica of the primary current scaled down. Now, these errors can be very small or large depending on many factors, such as the fault current levels, the type of CT that you're using, the accuracy class of the CT, and so on and so forth. So we need to develop some form of 87 or current differential algorithm that takes into account this realistic but non-ideal behavior of the CTs. So throughout this lecture, I'm going to be using this example that we drew before. So for example, imagine that there's a fault on the bus in the one line below, or rather just outside the bus. So for example, in this one line that I've drawn over here, let's say that there's a fault over here on feeder number 1 on the left. The CT on feeder 1 will see the total fault current contribution from the two sources, in this case from this transformer and this transformer over here, and from the other feeders as well if they were networked, but in this case we're going to assume that they're radial. So the fault current that this CT over here is going to see, again, is going to be the summation of the contribution from both sources. And so because of this CT is more prone to saturate than all the other CTs in the scheme, since it has the most fault current flowing through it. So because of that, it may not reproduce an accurate secondary current, while some of the other CTs in the scheme may reproduce an accurate secondary current. So to mitigate this possible difference in CT performance between different CTs that are involved in our scheme, a technique that's called the restrained differential protection element was developed in the past. And this technique is implemented in most modern bus differential protective relays, although its definition may be different between different manufacturers or even between different models of the same manufacturer. Now in this lecture, we're going to be discussing the Schweitzer SEL487B restrained differential element as an example. All right, so first let's define two quantities for our bus differential protection scheme. And again, this is something that modern protective relays do. So we're going to define what's called the operating current, which is also referred to as the differential current sometimes, and the restraining current. And let me actually write it over here. So we're going to define what's called the operating current. And again, this sometimes is also called the differential current. And we're also going to be defining what's called the restraining current. And again, these definitions vary per manufacturer or even per models of the same manufacturer. In this case, we're going to be talking about an SEL487B specifically. So the SEL487B specifically defines the operating current, and let me actually switch colors here to white. It defines let me actually rewrite this. So let me say in the SEL487B. And again, you always have to reference the instruction manual for the specific relay that you're using. In this example, we're going to be using an SEL487B. But the 487B defines the operating current, which I'm going to call I up, as the addition of the currents through each one of these CTs, and then the absolute value of that whole addition. So in other words, let's say for example that I'm taking the A phase current, and this by the way is done per phase. So let's say for example that I'm trying to calculate the operating current on the A phase in my differential scheme. Then the relay is going to take the current on the A phase for input number 1. It's going to add that up with the current on input number 2, A phase, and then dot, 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 and as many inputs as we have. So I'm going to say IA1 plus IA2 plus dot, 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 plus IAN. And notice that we're taking the absolute value of the whole summation. Now the restraining current, on the other hand, which I'm going to call IRST for restraining, and again I'm doing this for A phase, that's going to be the addition of the absolute values of each one of the inputs. So IA1 absolute value plus IA2 absolute value plus ... absolute value of IAN. And these of course are all phasors. So notice here again that the operating current or the differential current is the absolute value of the addition of all the phasors, while the restraining current is the summation of the absolute values of the individual currents. This is an important distinction. And again, the way that the relay defines what the operating current is and what the restraining current is depends on the relay that you're using. Different manufacturers and different models within the same manufacturer have different definitions. For example, some SCL relays divide the restraining current by 2. And some GE relays, for example, use the maximum of any of the inputs as the restraining current. So it's always good to reference the instruction manual for the specific relay that you're using. And again, these definitions are specific to the SCL 487B protective relay. Now from this, we can make two observations. One is that the operating current, again, is the net current in the bus, meaning difference between what comes in and goes out of the bus. Now this, under normal operating conditions, in other words, when there's no fault in the bus, should technically be 0, since the currents that enter the bus always leave the bus. Now, on the other hand, the restraining current is the addition of all the currents, which will increase with load and during faults. Again, this is an important point, and that is that the restraining current increases for heavy loads or during faults. Now, let's run through 3 different examples. First, let's calculate what the operating current and restraining currents would be for an example where the bus is heavily loaded. Then let's do the same thing for an external fault, and then let's do another example for an internal fault. So let me actually use this same one line that I have drawn over here, and let me erase this, and let me switch back to red, and I'm gonna say here example 1, heavy load. So let's say, for example, that all these breakers were open. So I'm going to say these are open circuited, so they're not in service. And let's say that the current that flows through this breaker is 1000 amps at 0 degrees. Same thing for this breaker over here, 1000 amps at 0 degrees. And again, if this is just load and these other breakers are open, that means that the entire current then would flow through this feeder over here. So the current that flows through here would be 2000 amps at 180 degrees. In other words, the addition of the current that flows through the 2 main breakers. So in this case, let's calculate what the operating currents and the restraining currents would be. Again, using the definitions that we've defined over here. So the operating current, which I'm going to write over here, I up A, again, is the addition of all the currents, and then we're taking the absolute value of the whole thing. So in this case, we would get 1000 amps at 0 degrees plus 1000 amps at 0 degrees plus 2000 amps at 180 degrees. So I'm taking all the current inputs and I'm adding them up together and then taking the absolute value of that. And of course, if we calculate this, we would get that this is equal to simply 0 amps. Now the restraining current is the addition of the absolute value. So 1000 angle 0 plus 1000 angle 0, absolute value of this, plus absolute value of 2000 angle 0, or rather angle 180. So if I calculate this, I get that this is equal to 4000 amps. And again, notice the point that I was making here earlier, and that is that under normal conditions, in this case under load, the operating current comes out to 0, and the restraining current, because we have a heavily loaded bus, comes out fairly high. Now let's say, okay, what happens if instead of load, so let me actually erase this. What happens if we have a fault on the bus? So we have a fault over here. And remember that for this example, we're saying that feeders 2 through 4 have their breakers open, and feeder 1 has the breaker closed, but it's a radial feeder. So it does not have a source on the load side. Now, just as an example, let's say that the fault currents were 5,000 amps at 0 degrees, and let's say that it was 4,000 amps at 0 degrees over here for source number 2. Now in this case, again, because feeder 1 is radial, there's not going to be any contribution from feeder 1. So this is going to be 0 amps, and all the other feeders, of course, are open, so they won't contribute any fault current either. So let's calculate what the fault current, or rather what the operating and restraining currents would be for this example. So let me say over here, example 2, internal fault. So there's a fault in the bus. So for this case, of course, we would want our bus differential scheme to operate. So we're going to do the same thing. Let's calculate the operating current, I up A. That's going to be equal to, in this case, 5,000 amps at 0 degrees plus 4,000 amps at 0 degrees plus 0 for all the other inputs. So this gives us 9,000 amps for the operating current. Now for the restraining current, IA, we're going to do the same thing, but we're going to add up, or rather take the absolute values of each number first and then add them up. So we're going to get 5,000 angle 0 degrees plus 4,000 angle 0 degrees. And this, of course, gives us 9,000 amps. So in this case, both the restraining and the operating current are both equal to 9,000 amps. And then lastly, and this is going to make more sense once we actually talk about the operating characteristic of the 47B, but first I want to calculate these values. So lastly, let's do the same fault, but instead of being on the bus, it's going to be just outside of feeder 1. So I want to say example 3, which is going to be an external fault. So in this case, going back to the one line over here, instead of having the fault current, or rather the fault over here at the bus, we're going to have it at this location over here, just outside the CT, this CT over here, which is part of the differential scheme over here. So in this case, then the current that flows through that CT is going to be the addition of the other two, so 9,000. And because of the ways that the CTs are connected, this is going to be 180 degrees. So it's going to be, of course, the addition of the other two, and it's going to be shifted 120 degrees because instead of entering the bus, it's leaving the bus. So in this case, let's do the same thing. Let's recalculate the operating current. And so we can see then that the operating current, for example, I up A is going to be, again, 5,000 amps at 0 degrees plus 4,000 amps at 0 degrees. But now plus the third input over here, which is 9,000, this one over here, 9,000 at 180 degrees. So now we need to take that one into consideration as well. So that's going to be, again, 9,000. Let me rewrite this, 9,000 angle 180 degrees. And so now if we add all of this together, we would get that the differential current, or the operating current, is going to be 0 amps, of course, as we would expect, because this is an external fault, not in the bus. Now the restraining current, let's calculate that as well. So that's going to be 5,000 amps at 0 degrees plus 4,000 amps at 0 degrees plus absolute value of 9,000 amps at 180 degrees. And so this is going to be 18,000 amps. So again, just to recap, example number 1 was a heavily loaded bus. We got that the operating current was 0 amps because, of course, the bus is not faulted. The restraining current was 4,000 amps. Now, for example number 2, we had an internal fault, in which case both the operating and the restraining current were equal to each other, and they're equal to 9,000 amps. And for an external fault, now we have 0 amps for the operating current and 18,000 amps for the restraining current. So now let's use this number and let's actually talk about how the SEL 487B declares a trip or a no trip based on its what's called a restrained differential element. So let me actually switch colors back to white. So now this is one of the most important parts of this course, and that is the definition. So let me put it over here. The definition of the restrained differential element in the SEL 487B protective relay. So what the SEL 487B really does is it takes this operating current and the restraining current and it plots it in a characteristic from which it determines whether to declare a trip or to restrain, or basically do not trip. And that's defined as the following. So let me actually put a pair of axes over here. So let me do this right here. And so the SEL 487B defines the trip no trip zones as the following. So we're going to have the operating current here on the y-axis. We're going to have the restraining current over here on the x-axis. There's a minimum amount of differential current or operating current that needs to be measured before it declares a trip. This is the 087P setting in an SEL 487B relay. So let me actually put that over here. And there's also what's called a slope setting, which we're going to talk about here in a second. But basically, there's a sloped element over here. And let me switch colors back to red. And so the trip, no trip regions, or the operate and restrain regions of the SEL 487B relay are defined as this. So we basically have this characteristic over here, and anything above that line, so anything over here, is going to be declared as a trip, which again is oftentimes also called operate. And anything in this region is going to be no trip, or also sometimes called just the restraining region. So the operating and restraining regions. Now notice here that again we have the restraining current in the x-axis and the operating current in the y-axis. And here again we defined two settings. We have this setting over here, the 087P setting, which essentially tells us there's got to be at least a minimum amount of differential current to operate this. But there's also this sloped setting over here, which in the SEL 487B really is either slope 1 or slope 2. Here we're just going to talk about one slope just to keep things a little bit simpler. But basically this defines how sloped is this characteristic. In other words, if you have a higher setting, then the characteristic will look like this, or you can change it and make it like this. So you can make different settings, basically make it more sloped or less sloped. And you can also play with this 087P setting, which defines the minimum amount of differential current that needs to be in place before the relay even considers comparing to the slope setting. So again, notice here that during heavy loads and during faults, the restraining current is higher. What this does is it causes the necessary operating current to declare a trip higher than when the restraining current is low, again, because of the slope setting. So in other words, what I'm saying here is that, let's say for example, that you calculated the restraining current to be somewhere around here. Let me actually move this up a little bit. So in this point, if your restraining current is over here, then the amount of differential current that you need to trip would be this point over here. Now, if you have more restraining current, so let's say that your restraining current is somewhere around here, now the required amount of differential current to operate is over here. It's much higher. So the higher the restraining current is, the more operating current you have to have in order for the relay to declare a trip. This is an important characteristic of the restrained differential element in any relay, but again, here we're talking about an SEL 487B relay. So again, the combination of a slope setting and the operating/restraining characteristics of the SEL 487B 87 element make this element more secure in conditions where the CT is more prone to saturate, or in conditions where the performance of the CT can be compromised. In other words, during high fault current magnitudes. And it does this by increasing the amount of operating current that's necessary to declare a trip. This is an important concept, and again, going back to the fact that some CTs may see higher current than others, like in this case, for example, feeder number 1 over here is seeing a higher current than the two main breakers, and of course, higher than the other feeders, which are open circuited. So that CT is more prone to saturate and therefore not reproduce a secondary current that's a perfect replica of the primary current. And so there's going to be errors that are going to be introduced when that happens, because now you have two CTs that are properly reproducing the secondary current and one that's not performing as well. And so by having this restrained differential characteristic, what we're doing here is we're essentially saying, well, when there's high fault current magnitudes, or just high current magnitudes in general, the amount of necessary operating, or sometimes called differential current, necessary to trip is going to be higher because you have higher currents, and therefore it's more likely that your CTs saturate, which essentially means that you're more likely to interpret the fault as internal because one of the CTs might be not performing as well as the other ones. So that's why we need what's called a restrained differential element, which again, the SEL 487B implements in the way that we've defined here, but all the relays have very similar characteristics. It might have different definitions for what it calls the operating or the restraining currents. Those change per manufacturer or even per model within the same manufacturer. For example, the SCL487B and the SCL387B have different definitions for the restraining current. So you always have to reference the manual to see what exactly the relay is taking as the operating current or the differential current and the restraining current. All right, so one last comment that I want to make before we move on to the other type of protection for buses, which is the high impedance voltage differential element, is that in this example, we have used primary currents and we haven't talked about really much about the CT ratios and the polarities of the CTs. Now, when you're developing settings for a protective relay, the CT ratios, of course, are going to matter and the polarities also matter, so you need to take that into account. Most microprocessor-based relays usually have settings to compensate the mismatches in CT ratios and polarities when needed. And we're going to discuss this later on in the example of using the SCL487B to actually develop settings for protecting a substation bus. But just as a quick introduction over here, let me actually erase this. Notice over here that the ratios of the CTs in the main breakers, this one over here, let me actually switch colors first. So this CT ratio over here, for example, is 1200 to 5. This one is 1200 to 5, but these are 600 to 5s. So the relay needs to compensate for that difference because, in other words, 1000 amps flowing through this CT is not going to be the same secondary wise as 1000 amps flowing through this other CTs on the feeders because the ratios are different. So there's settings in the relays where you can tell it, okay, which input has which CT ratio, and the relay internally compensates for that. The other thing that it needs to know is the polarity of these CTs. So again, notice over here that we have polarity marks over here and over here, over here and over here. This is typical where the CT is quote unquote looking into the bus. Notice over here that the polarities are always on the opposite side of the bus. So in other words, for these CTs over here, this one and this one, we have the polarity sides on the top side of the CT, meaning it's looking into the bus. But for these CTs on the feeders, it's on the opposite side. It's on the bottom side because again, we want current flowing into the bus to be considered as positive. So again, both the CT ratio and the polarity of the CTs matter in a bus differential protection scheme. And again, we're going to be talking a little bit more about this in detail in a later lecture where we actually take a look at an example on how we can develop settings for an SCL487B relay.